Welcome to the Thomistic Institute podcast. Our mission is to promote the Catholic intellectual tradition in the university, the church, and the wider public square. The lectures on this podcast are organized by university students at Thomistic Institute chapters around the world. To learn more and to attend these events, visit us at thomisticinstitute.org.
So there have been roughly 75 versions of this talk in my head over the last 3 weeks or so, and at least 10 in the last 2 hours. So we'll see exactly where this goes. First, some framing quotes. I was very pleased when Dr. Hastings had a quote from Richard Feynman, because while philosophically there are odd little quips he makes, pedagogically he's just an amazing teacher of physics. I spent a lot of time reading his lectures on light and QED to remind myself of what I had forgotten, so it was very helpful. But in doing that, I came across a quote which struck me interestingly. It says, "Physicists always have a habit of taking the simplest example of any phenomenon and calling it physics, leaving the more complicated examples to become concerns of other fields, say applied math, electrical engineering, chemistry, or crystallography. Even solid-state physics is really only half physics, because it worries too much about special substances. For instance, one of the important properties of crystals, or most substances, is that their electric polarizability is different in different directions. But in physics, we usually start out talking about the special case in which the polarizability is the same in all directions to make life easier. We leave the other case to some other field." So I don't start this just to poke fun at the physicists. I'm doing this to poke fun at everyone, because that's a very interesting quote by Feynman. But I would also add, Thomists always have a habit of taking the simplest example of any phenomenon and calling it natural philosophy, leaving the more complicated examples to become the concern of other fields. And this is in some ways just repeating a quote from Ludwig Wittgenstein. I cannot at all claim to have read much of Ludwig Wittgenstein. This is Michael Gorman pointed out to me when I wrote a paper on apples for a class on unity of substances. And there's this just what I think is just a very huge, very important idea. The main cause of philosophical disease is a one-sided diet. One nourishes one's thinking with only one kind of example. And I think this is, I've seen this in myself, both as a physicist and as a philosopher. You know, having been trained in theoretical particle physics, I joke, and it's only kind of a joke, that like I'm really only good at dealing with maybe 6, on a good day, maybe 8 to 10 electrons. And beyond that, I'm useless. That's what I'm really good at. And beyond that, I got to be a little careful. And even as a philosopher, I think there's a certain sense of like the kind of the sorts of examples, the kind of thinking that goes the way that I learned and a lot of the conversation around philosophy of nature among Thomists is like there's a sort of standard set of examples which are both very, very useful, but then also can become clouding. I think there's a little bit of this, and it's kind of come up in these conversations, that one of the things that I love about these kinds of events and the last 4 years of being at Angelicum, working on the product on science and religion there, is I've learned more science in the last 4 years than I had in a long time. You know, I learned a ton of physics in graduate school, but I've learned a ton of condensed matter physics, quantum chemistry, biochemistry, molecular biology, ecology. I'm not going to claim I'm an expert in those things, but it's helped me to recognize my own kind of siloing and my own kind of blind spots about what the best kind of example for a particular sort of thing is. So motivated that, of the need for multiple examples, I'm going to end up giving one very specific example and try to lean heavily into that. This is not to say that this is the only example, but I think it's trying to intentionally pick a very concrete situation and try to apply the philosophy of nature to it. This is another thing that I feel like, particularly for Thomists, is important to kind of dig into the details, and sometimes very concrete situations for trying to dig into those details can be helpful for intuitions moving into other examples. To put my cards on the table, I am a Thomist who believes in material substances. I agree, I take the horn of the dilemma that Steve proposed, that I don't think that photons or electrons or most atoms are substances proper. I think there might be some molecules that are substances, but it depends on the kind of molecule you're talking about. I mean, insofar as there's a certain sense which you can talk about like a diamond as a molecule, just like a big macromolecule, I think that's clearly a substance. Insofar as you're talking about a water molecule in liquid, I'm not quite so sure I'd want to label that as substance. That might be part of something else. And I'm eventually going to try to get to that a little bit. So what I'm going to try to motivate is lean into some questions from physics, kind of building on things that Steve and Chris talked about, but sort of honing in on a couple particular maybe aspects that they either mentioned but might not have focused on, and then try to kind of dig into a particular example to try to think through what would it mean to be the sort of Thomists who thinks that macroscopic objects like human beings and dogs and cats and rocks and crystals are substances. What should you say about light in that case? I'm going to try to look at a particular example to kind of dig into that. So the plan then is to walk through a couple different points kind of as a framing device. The first is actually just to make a kind of reflection about like what is kind of weird about light just from the perspective of a particle physicist that at least sort of pushes in a direction of saying that there's something different about that than other things that particle physicists tend to focus on, other particles. Then I'm going to list some things Aquinas got wrong. There's lots of them, but sort of some specific things that claims he makes about how light works that just aren't right, but that actually reveal something about how we should think about how light works. And then I'm going to say a few things about what a siloed scientist might get wrong. And here I am primarily accusing myself as someone who primarily tended to think of like high energy particle collisions as the fundamental way to think about nature. It's like that's a really great way to think about high energy particle collisions and other things too, but probably not the best way to think about an amoeba or a paramecium or a cat. There's just so many electrons in a cat, it scares me. And then I want to try to like dig into the part I kept debating about in rewriting of how deep of a hole I'm going to dig for myself, of trying to kind of motivate a still in progress, but trying to like a motivated picture of what light might be for a Thomist who doesn't want to say light is a substance, but that substances are these sorts of macroscopic objects. Okay, so why is light different for a particle physicist? I mean, in a certain sense, when I was a particle physicist and programming simulation for particle colliders, there wasn't much difference between a photon and an electron. It was just like which flag I did on my calculation code, and that just meant like, okay, a slightly different charge, a slightly different spin, a slightly different vertex. In one sense, we look at the fundamental particles of the standard model of particle physics. The way in which physicists tend to identify and distinguish them is by their quantum numbers. And this is a subset of these. So you see the mass, you see the charge and the spin quantum numbers. There's other quantum numbers too, but notice the photon, 0, 0, 1. I mean, I don't know if you've ever done math before, but like zeros and ones are really useful when you're doing math and adding and multiplying things. So there's something kind of like interesting about that. It's not the only 0, 0, 1. I mean, I don't know how small. The gluon's got a 0, 0, 1 there, but it's hiding what Steve was talking about, the color charge. It has conserved internal quantity of color charge such that, which makes it different than the photon in an important way that was related to what Steve was saying, but I think leans into something. And so what does this mean about light as a field, particle, entity particle physicists talk about? It has no conserved internal quantum numbers, right? It has no charge, it has no color, it has no lepton number. Why is that important? Well, if you had a charge and you're dealing with an electron and you want to do something with the electron, you've got to get the same charge out at the end. So if you start with an electron, you've got to end up with something that an overall thing negatively charged at the end. Whereas you can add as many photons as you want, and it doesn't actually, you don't have to worry too much about changing the charge. Insofar as there's conserved lepton numbers for certain kinds of interactions, maybe not all. Insofar as you have leptons going in, you have to have the same number of leptons going out. Pache some different kinds of interactions. But just basically, insofar as it doesn't have internal quantum numbers, there are less restrictions on what it can interact with, and what you don't always have to get a photon out when you put a photon in. Roughly speaking, if you put an electron in, you better get an electron or a neutrino or something else out. Again, it might turn into a different fermion in certain limited cases, but it's easier to produce photons than a lot of these other particles. It has no mass. What does that mean? Well, it's never at rest, ever. Now again, in a certain sense, no particle is ever at rest, but there's a certain sense in which we can put various particles at relative rest with respect to one another. No photon is ever at relative rest with respect to any massive particle. no photon is going to enter into a kind of stable bound state with any other particle, at least not in the way that we imagine bound states in relations between even like electrons and positrons or electrons and protons. That insofar as one doesn't have the charge, but it doesn't have the self-interaction, it doesn't have the sorts of things we would want to make it into a bound state. We kind of like, you make them, they go places, and then they go away. The other is it's spin one. No Pauli exclusion principle. So you can cram as many photons as you want into a state as you like. That's why there are lasers, but no Easers. There's no electron assisted amplified simulation, whatever the acronym is. You can pump a ton of electrons of the same kind into a small space. And so there's just less restrictions on what are the conditions when photons can pop in and pop out. So it just is really easy to make light. You just need a charged thing, and you need to just take some energy from it. And it's really easy to destroy light. You just need a charged thing and give it a bit of energy. So it's really easy to make light in a way that it's not easy to make W bosons, Z bosons. It's not easy to make gluons even, for all sorts of QCD reasons. So that's interesting in a certain sense. All of the other particles are, at least in some sense, harder to make, and in some sense have a kind of like open to, well, not all, many of the particles are open to a kind of collective stability in the way that just photons aren't. They kind of are what they are, do what they do, come into existence, bump into some things, and go away. Okay, so I just want to put that in the background. So what are a couple of things Aquinas got wrong? We could go on a whole long list about the speed of light, first things like that, but I want to focus here on, he has this sort of trifold distinction of like kinds of beings and how they relate to light. All material beings are one of these three. There are luminous things, that this lux in the Latin, have an active quality of a source of light. So this is stars, to a lesser, or stars, the sun, to a lesser extent fire. There are diaphana, transparent objects, the passive quality of being receptive to light. So this is just transparent things, air, crystals, transparent crystals, water. And there's opaque things, the inability to produce or be receptive to light. This is things with surfaces that are colored. But every physical body is luminous, transparent, and opaque. It just depends upon the wavelength, frequency, energy, polarization of the light photon in question, right? Every physical body, and I'm going to use that term broadly and then sort of hone on it more. But if there's a organized physical massive body that is above absolute zero, which is everything, it's giving off light. Maybe very little, and maybe at very, very weak, low energy, but it is a source of light, source of electromagnetic radiation. And everything is transparent to some light and not to others, depending upon the wavelength. So these categories are common to all bodies and depend upon, as we'll see, the interior structure as we're going. So again, at least thermal radiation, and depending on the kind of structure, there might be other modes in which you could produce light. So if you have a certain kind of electrical excitation, running current through things to heat them up would be a thermal case. The plasma case in the fluorescent bulb, I'd have to think about a bit more. But there's ways that things produce light. The sun, being roughly 5,700 Kelvin, produces lots and lots of visible light, which is good. And we are much, much, much less than 3,000 Kelvin. I mean, we're down at the scale of just giving off some infrared radiation, but that's why infrared cameras work. That's why these things function. The other thing is that every physical body is more or less transparent or opaque depending upon the wavelength. The sky is a massive transparent body to some wavelengths and completely opaque to others. So here's a kind of picture of the electromagnetic spectrum, and you see there's, it's a little small, but the radio waves, microwaves, the different structures, and you see this sort of grayish background plot. That is the plot of how much absorption, like how opaque the atmosphere is to various wavelengths of light. So almost all low radio waves, like there's a sort of open space in radio waves, which makes radio telescopes work, for ground-based ones. Sort of microwaves through, kind of certain infrared is mostly blocked out, and then it kind of gets messy because now we're getting into weird things about the particular chemical structure of the atmosphere. Then you have a nice, neat, fairly clean gap for visible light. And then there's just almost immediately opacity to a lot of ultraviolet light. Not all, but a lot of ultraviolet light. Now, in one sense, that's just interesting. And I'm going to primarily focus on that, just the fact that even something that the sort of thing that we just presume to be transparent is transparent depending upon the kind of electromagnetic radiation that's involved. Even you and I are transparent, and parts of us are more or less transparent to X-rays. So bones are less transparent to X-rays, and flesh is more transparent to X-rays, which is why X-ray medical imaging is so useful. So what determines sort of which wavelengths, which kind of light, what energy level of light, and again, there's a whole conversation about polarization in certain contexts, but I'm going to kind of set that aside. Something is more or less transparent to is due to the chemical constitution. So this is the beginning of lots of words in scare quotes. So these scare quotes are intended to be heuristic starting points that I think can be fleshed out either or both in the kind of bit more science detail or a bit more philosophy detail. And so I'm perfectly happy to be poked on them or any other words. But just these are the ones I noticed when I was trying to summarize my thoughts on this. But there's something about the arrangement of the atoms, nuclei, and electrons in molecular structures that change how something reacts. So on the left side, you have for like very high energy photons. So this is sort of UV and up for carbon, and on the other side for lead. So it's a little bit different for the two of them. It's a little bit side point, but there's different processes that are going on here. So on the weird peaks you see up here are like photoelectric effect aspects. So as different energy level, as the photons get high enough to knock off more and more electrons, you get these weird little spikes in the edges in how much light something can absorb. Down here you have what's called Rayleigh scattering and moves into Thomson scattering depending on the context, which interestingly enough, if you just had a diffuse sea of electrons and nothing else, the cross-section for all light down below that level would be the same. All light would interact with any of the electrons out there at roughly the same rate. Here you get into interesting, so this sort of bump here that's down low, there's sort of primarily a sort of flat Thomson scattering with like the actual structure of the atom on top of it. So these are the spikes I was talking about. There's sort of interesting issues about like, what if you just had a bunch of electrons interacting with light that weren't bound to anything, how would they act? Here you have Compton scattering. This is where photons are giving momentum to electrons in various ways. And then up here, what you have is photon-photon scattering. So photons generally don't interact with photons, and there's no photon-photon vertex. But if you do funny things, and you have enough energy, you can take two photons and get an electron and a proton out of it. So the problem is you got to have enough mass to have a stable electron and proton. And so what's going on here is the high energy photon is interacting with the electric field of either an electron in the atom or the nucleus of the atom, and producing a pair of producing a electron-positron pair. So just say like at high energy things get really weird. There's a certain sense in which the vacuum of space is opaque to certain very, very, very high energy photons, because there's enough background light, very, very little of it, but enough that at a certain high level TeV, it's only in a matter of time before that high energy photon is going to hit something and produce electron-positron pair. So again, depending on the scale, this might be like galactic scale or even universe scale, but there are certain kinds of light that even the vacuum of space is opaque to in some sense. Okay. As we get down to lower wavelengths, so now we're looking kind of into the direction is flipped here. So there's ultraviolet on the left here moving into infrared and lower wavelength. But we see, right, so even water, which we take to be a nice transparent thing, is transparent for visible light, but it's not transparent for ultraviolet light, and infrared light gets messy depending on the context. And a diamond is really nice in the visible region, but there's weird higher edges in the UV range and weird infrared phenomenon where it like interacts with phonons in the diamond itself. So even the things we take to be the most transparent are only transparent depending on what kind of light. Okay, so what are some things that a siloed scientist might get wrong? And I say this because I just feel like I've gotten these wrongs before. These are things I studied in studying physics and like did calculations about, moved on, and got really into particle physics and kind of like forgot the context about, or never really dug into the details. Like, oh yeah, I could probably, like, I see where that's going. Yeah, I see how you would sort of generally do what you're doing there. And so I want to focus on one particular kind of phenomenon, namely what happens when light of some particular wavelength enters a body that is roughly transparent to it, that it can pass through in a stable way. Well, we get, as we've seen, the bending of light and the kind of phenomenon of slowing of light that we refer to as the index of refraction. Well, what actually is causing that? Like there are explanations that can give you the right answer for where light is going, but what is it that produces that effect? And there's sort of two particular powerful ways to describe this, one more leaning into the classical and one leaning into the QED side, and I want to kind of present both of them. And the first is just, and again, if you're at all interested in the classical theory of light, I highly recommend this 4-part series. So this guy's shtick is he's a mathematician who does really fancy animated videos of mathematical stuff and some of his physical stuff. So he has these like, I mean, he's literally just like wants to play around with a tool he made to show electromagnetic radiation, but he teaches it something along the way. So you see patterns like this. The little ball are electrons, and he's moving them around, and the sort of fluctuation up and down arrows is the change in the electric field through space. And he's primarily focusing on the plane. So notice here he starts with a couple, and you see a kind of like nice pattern here with this line, but it's still kind of bumpy. You take an entire sort of sheet of these, and you start to get something like a plane wave. You're starting to get the kind of plane wave that we recognize from Huygens. So what happens, so just for the sake of time, when we talk about the index of refraction, one way of quantifying what's going on is that as light enters into a medium, its phase is shifted back and its wavelength shrinks, and it moves slower. But like, why? Why? And so he just posited initially that just like, okay, imagine there are lots of layers in whatever the medium is, and at each layer, you kick the phase back. Why the heck would that happen? Well, you start with a simulation like this with layers and layers of sheets of electron the electrons are being influenced by the red field going in. You see the one wave, but it's filling space in a neat way. And then the motion of the first sheet produces the little blue wave. But the two light waves, they interfere in such a way, they're of the same frequency, but they interfere in such a way that the net effect is this really weird wobbling on the left and a kind of like weird phase shift right at the beginning. So the stuff going left is ultimately talking about reflected light, which I'm not going to go into as much detail about. But the stuff on the right is that one layer causing a phase shift. And you add layer after layer of that, and the net effect is that, each new layer shifts the phase, the position of your oscillation back. And so the overall effect, as you average this out on a big scale, is that the speed of the wave slows down, the frequency stays the same, the wavelength shrinks, the speed slows down. So again, way more stuff you could say about that. And if you're curious, I highly recommend the whole series. He does a great job. But the thing I want to say is, like, so how do you figure out what the index of refraction is in a classical sense for a big massive body? You figure out where all the electrons are and you start shaking them. And you have to shake all the electrons. First the first layer, then the next layer, then the next layer. And at least in the simplest version of the calculation, it works out really nicely. Because obviously, all physical things are structured with a nice cubic lattice of electrons, right? So that's classical physics, right? We're a good modern quantum vehicle. So how do we go about doing this in QED? So here's a couple of slides or a couple of pictures from Feynman's book QED, Quantum Electrodynamics. I highly recommend it. It's a popular lecture on quantum electrodynamics. which sounds like it would just be bad, but he actually, because he's presenting the mathematics in a way that is accessible without getting into the details. The thing I want to point out is the calculation you do in quantum field theory for what is the path of a photon moving through, and so I'm conflating it too few things. So first we're talking about the index of refraction in the sense of it bending when it hits the surface. And to figure out the right answer here, you just say, okay, let's just take every path that the photon could take to get from point A to point B. And each one is going to be slightly different. This kind of came up in a little bit. And in one sense, this is step one to the least distance principle, where you calculate all of these, find the minimum, and that's your answer. In quantum mechanics, it's not quite like that. It ends up being that in this particular case, yes, the shortest distance and the most contribution comes from what seems to be the lowest least action, the least time path. So sort of the x down here corresponds to roughly the correct diffraction, but you actually need at least some of the contributions of the stuff next to it. And ultimately, to get the full answer, you need to include more extreme versions of that that seem to be completely counterintuitive. So here we see there's a certain sense of if you're doing this in classical, you would just pick the bottom point and be done with it. In quantum, you actually need to sort of consider the contribution from all of these. This gets really weird when you want to explain a diffraction grating, because in a diffraction grating, you start randomly grabbing. To be very short, basically what you do is you take all these vectors, add them up together, take the total, square that. That's the probability of something happening. That's way too fast. He explains it much better in the book. But the point is that insofar as some of these vectors are pointing in random directions, they're not really contributing much. They're kind of canceling each other out over and over. Whereas these 3 or 4 near the middle are roughly pointing in the same direction, making a much longer vector, and a higher probability. When you do weird things with diffraction grating, you start just randomly grabbing things that were canceling each other out, and they're not canceling each other out anymore. So suddenly you're getting strange contributions. That's how you can explain, in quantum field theory, strange things about diffraction, strange things about lights turning corners. When we're talking about just the speed of light transmitting through a medium, you do the same thing. In a certain sense, this version here is a simplification of what we have over here, because you wouldn't just take the middle, the straight line points. You would actually calculate every single spot on every single aspect of the glass you're talking about or whatever you're dealing with. And you add up all their contributions. Now, insofar as he's done this calculations, he kind of knows the middle one's primary. So you get a really big contribution from the amplitude as if the light just didn't hit anything. But you get lots and lots of little contributions for what if the light hit this electron? What if it hit that electron? What if it hit that electron? What if it hit that electron? When you add all those things together, if it's transparent, it doesn't change the amplitude, but it does actually change a feature such that the light travels slower. Again, he gets super agnostic about this, what that means. But the point I want to make here in trying to summarize QED in 25 seconds is that the way that we understand how this macroscopic phenomenon works involves engagement of either the waves as a whole or even individual photons with a huge number of the electrons involved. And it depends on where they are and how they're arranged, what the actual index of refraction is going to be. So we quantify the way light tends to pass through, reflect, or be absorbed for a given wavelength by the index of refraction. Turns out it can be complex. That's what helps to clarify issues of absorption. But the value of that index of refraction of a body is deeply dependent on how exactly the electrons are related to the nuclei and to one another, and how they're able to vibrate and move about. But working at the details of those relationships and its effects on the index of refraction is really, really difficult to do. It's way too many electrons for me. But condensed matter physicists, and quantum chemists, approach these problems by various numerical methods, generally involving kind of positing the nuclei as they're just big balls of charge that aren't going anywhere or not moving very much. Quarks, gluons, whatever, just big balls of charge as your nucleus. Not even really protons and neutrons, just big ball of charge. And then that determines a kind of Coulomb potential, a electromagnetic potential that the electrons sit in, and then you try to build up approximate solutions to the Schrodinger's equation for that potential. You kind of try to get the lowest energy states possible, and then you see what effect that has on where the nuclei are, and if they shift around a bit, then you do it again, then you do it again, then you do it again, and you get really good results for some kinds of complex structure. I'm oversimplifying something I've never done and have had described to me about 3 or 4 times, so I'm sure there are probably people in here who are much more expert at that. But the point I want to say is that, generally speaking, the electrons in those complex systems end up being, to get the math right, you have to treat them as entangled on some scales and indistinguishable in important ways, such that we really shouldn't be talking about the activity of this electron or that electron. It's not as if, okay, well, first, there's the 1s electron on that carbon atom, and then the other 1s electron on that carbon atom, and then there's the 1p and the 1p. Well, now it's actually, maybe it's a 2sp orbital. You are engaging with the electrons of a collective, at least at some scale. So this is something that, the kind of calculation that, in principle, I learned how to do as a particle physicist, but never actually had to do. But there's a funny thing, because when I talked to when I learned about this from people who do it much better, the condensed matter physicists, so what's the Coulomb attraction? What's the Coulomb potential? It's just the Hamiltonian you plug into your Schrödinger equation, right? It's a fact of how nature works, and we take it. But there's a story about how that works in quantum field theory, and it looks like this. You have a proton and an electron with just tons of photons binding them together. What it is to be, this is a sort of more complicated version of something that Steve mentioned up. This is again from Feynman's QED, that there is a kind of weird mess of photons binding this proton-electron together. We refer to them as virtual photons for various reasons, because not all of them are actually traveling at the speed of light. Not all of them are, technically speaking, massless, depending on how you're thinking about it. It's weird, it's strange, but you need to include that. And again, as a brief defense of this, I'm going to talk about something that Steve mentioned, which is that anomalous magnetic dipole moment. But I want to just lean into this briefly, just to say just how horribly impressive this is, right? So the actual experiment that gets this data is a single electron trap with a very, 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 very stable magnetic field. And you then allow that electron then to spin around in that magnetic field. And there is a kind of energy transition between 2 different angular momentum states based off the inherent spin and the rotation, the cyclotron spinning of what's going on. And when you measure this, you get absurdly accurate data. You have very, very good precision on the experimental result, which is this number we saw. Sometimes they write it with the 1 in front, sometimes not, depending on how you want to coordinate this. The thing I want to say is that the bare level default simplest, pick the bottom of your Fermat's last principle, or your Fermat, least distance principle version of what you would say to this answer is, oh, it's just 0, or it's 1 in this context. Well, that's not right. So we got to do a little bit better. Okay, well let's grab the next one. So the next one does pretty good. It's good to 3 or 4 significant figures, and this was a huge success at the time. But how did we get all the way there? We calculated not only so this is referred to as second order. We calculated 4th order, 6th order, 8th order. It's 4 and then 6 and then I think there's 2 that have 8 maybe. And then there's this weird mass of 10th order things. So what are all these lines? All of these lines are potential virtual photons and electrons bouncing in and off of each other. And all of the complete set of numerical ways that you could take that one little vertex and glue it together to make a connection between a system where you have one electron coming in and one electron coming out, just interacting with this whole mess of virtual stuff. The thing is, to get the accuracy, you need to bring into bear all of these calculations. That's not to say that these things are real, and that means they're definitely not real in the particle physics sense of it, because most of them are not on mass shell. They're not acting like electrons and photons really should, in terms of the photons seem to have might have mass. The electrons might have different masses than they should, but you need all of these corrections to get that accuracy. So there's something about the natural world that this just weird, like child's drawing set of stuff is telling us. What exactly, that's not quite so clear, but there's something there about this idea of virtual photons and this sort of weird mess of like, well, let's just consider all the possible ways this could happen, see what those contributions are, and that helps us answer questions. So given that like very, very selective, broad background, I want to try to argue for what I think things a contemporary Thomist, namely me, might say about electromagnetic radiation insofar as you ask me now and not 20 minutes from now. But first off, electromagnetic radiation is a quality that adheres in a bodily substance. Okay, great. We've heard roughly that a little bit, and I think that is the right answer. I don't think the photon is a substance, and we'll talk about that a bit more. I do think it's a kind of quality, but I also think that just saying it's a quality is like, it's not enough. What kind of quality is it? What does that mean to have the quality of electromagnetic radiation? For the Thomists in the room, I'm going to lean into it being a sensible quality of the third species of quality. For all the physicists and chemists and biologists, I apologize. I lean into this to say, like, I think that's the right categorization. The problem is that Aquinas' way of thinking about these things isn't going to help us. Because for him, a sensible material quality in an inanimate substance, like a hunk of iron or diamond, all of the qualities of an inanimate body are homogeneous. So a piece of diamond, a piece of iron is just iron all the way down, right? Every quantitative part of an individual substance of iron, an individual hunk of iron, whether it's like you imagine taking a piece of it or actually take a piece of it, it is iron. It has a substantial form of iron and all the same qualities as the piece of iron had before. So there's no interior structure, it's the same all the way down. Living things are in no way, well, okay, for him, there's, no backup, yes. A living thing, animals, most animals, and I think you could even say this of all animals, are not homogeneous. And I think most planets are not homogeneous in the sense that any chunk of an animal that you take and actually remove from that animal is not going to be of the same kind anymore. Pace a few cases where you end up with something that could survive and become something like it was before, but it's at least going to start off being really, really wounded and needing to do a lot of healing. So you can't just remove pieces in the same way that I can just take a hunk of iron, divide it, and get the same thing over and over again. But that's just not how chemistry works, right? It has this, the same sort of substantial, like Aquinas had the same substantial form and proper accidents as the original at whatever scale you get down to. But this is not going to do for us because at least when we get down to, again, it kind of depends on what kind of substance you're talking about, what kind of in my head I'm focusing on inorganic crystals, metals, things like that. We'll get to organic chemistry. That's for next time perhaps. And many of these, like the properties of the conductivity of a metal, are going to be roughly the same down to near nanometer scale. I'd need to actually go back to my condensed matter physicist friend to verify exactly what that scale is. But you can take lots and lots of chunks of a piece of copper, and the interior properties of its density, conductivity, thermal conductivity are all, it's going to be the same. But it doesn't go all the way down. At some point, there is structure, and we need to say something about that. So what might a complex structured quality look like for Aquinas? In the inorganic world, we don't have examples of that. But it would be helpful to take an analogy from versions of complex qualities he does think about, insofar as organic bodies, organized living things, have qualities that adhere in complex organs that are not homogeneous, that have different kinds of mixtures that can have different qualities and therefore can act on one another. It's helpful to kind of think about that and what that means. So consider a sense power. So we'll take the sense power of hearing. Technically, that's a second species thing, but again, debate that for the Thomists later. But for Aquinas, what it is to be, like what the power of hearing is a part of the substantial form, or an accident in hearing in the substantial form of the soul of the living being, but that is particularly ordered to a particular subset of matter, which is the ears, the eardrum, some kind of like gap of air and nerves that connect to that. And so this is going to mean there's going to be this sort of localized, that quality of the power of hearing is going to necessarily imply a complex story of organization of material parts and different mixtures of material qualities. Localized in particular sets of organs, each organ being itself this like collection of distinct homogeneous mixtures of the four elements for him, with relatively fixed positions. Most of the stuff in us doesn't move around, some of it does, but most of our organs are kind of stuck to one another in a particular way. Between most of the organs, the power of hearing then is a quality that is sort of constituted in a particular way and depends for its activity on there being a kind of thin eardrum of skin containing a cavity of still air that can be moved, that is still in some ways protected by the sort of fleshy exterior part for various reasons, as well as the nerves that are going to link back into the brain. They don't work by electricity for him, but that's a whole other conversation. When actualized, the power of hearing is there in a silent room. The power of hearing is actualized by the reception of sound, a kind of physical vibration in the air. The physical arrangement of those organs starts moving and reacts with the motion of the air carrying the sound. And because of the material structure of how the eardrum is organized, it's the right kind of mixture of qualities that it can be beaten and vibrate with that air, the exterior air, and therefore vibrate the interior air and be receptive of sound in the material aspect of the reception of hearing for him. And again, all of those organs that are properly speaking there, that in some real sense for the power of hearing, can do other things as well. I can feel with the flesh of my ears. I don't want to feel my eardrum, but I'm sure it would be painful if I did. There are other kinds of actions and passions that they can undergo, in addition to simply being the ground for hearing. Okay, so that's interesting, but the parts of, and here's where I'm going to lean into just a very specific example. I want to think about a diamond, a particular macroscopic collection of carbon atoms that are covalently bonded together in a, that's not necessarily perfect, but like pretty darn good cubic lattice, maybe with a few impurities in there, but a good, nice, standard diamond. The carbon nuclei, electrons, quarks, gluons, etc., are not parts in the diamond in the way that organs of hearing for Aquinas or any other organ are in the living being, for two, probably more reasons, but at least two important ones. The relative position and organization of the field excitations. I'm going to lean into that way of talking about what we're talking about. We're talking about an individual electron or photon. Again, protons are a little bit different because they're collections of these things, but leaning into the field excitation is the particular structure there is relatively homogeneous in the way that my power of hearing is not, right? Whatever powers this chunk of the like the upper right part of the diamond has, the lower left part has as well, at least down to some scale. Parts of diamond are the same kind of thing with the same kind of activities because they have the same kind of crystal structure made of the same kinds of field excitations a long way down. Not all the way down, but a long way down. And then the position of particular parts is not fixed in the way that it is for an organ, and it's not even the same for all of the things we might talk about in a diamond, right? The carbon nuclei can be individuated and maintain the relative position stably, right? They don't actually, they're under relatively normal conditions, so like room temperature, normal pressure, the crystal structure of the diamond isn't undergoing random changes. Again, as you start to heat it up, it can start to break down. So there is a fact of the matter about this carbon atom being next to that carbon atom, or this carbon nuclei being next to this carbon nuclei, being next to this carbon nuclei. And insofar as you know where one is, that helps you to understand where the other ones are. The electrons are roughly numerically stable, barring some static charge, but cannot be individuated, as we were talking about, and only kind of localized as a collective. There's a story about where the electron density tends to collect more or less, but it's not a story about adding up the activity of each individual electrons, but just at least some collective or series of collective activity of these localized electrons. And there's some kind of virtual photon stuff going on. If you want to lean into that more in just like classical field sense or more in a particle physics sense, there is electromagnetic radiation doing something to make a diamond, even in the dark. So Thomists, myself included, throw around the Thomistic notion of virtual part or presence when talking about these kinds of things. I worry about that language just because the way Aquinas uses it, he's using it about homogeneous things, and we tend to forget the importance of position and relative position of these things. I think we'd actually learn a lot from quantum field theory, the quantum field theory notion of virtual as a kind of helpful notion of what might be going on about the presence of these sorts of things. And again, I think it's going to vary depending on where you're talking about stuff at the level of photons versus stuff at the level of electrons versus stuff at the, don't even want to get into the QCD of the quarks and gluons. Okay, for the sake of time, I'm going to jump ahead here. So I think that there's a way in which we could talk about the diamond being some kind of mixture of elemental fields whose position, with distinct elemental powers. Here I'm thinking about the mode in which the different fields act and react with one another. Again, I'm falling back on quantum field theory notion of what kind of interactions are possible, but you could talk about that in a different mode. In some cases, in relatively fixed locations, positions, virtual parts. In some cases, much more diffusely. And so the diamond has the material active power, a kind of quality by which it can emit electromagnetic radiation, given a particular temperature that it is. It is a power of the diamond as such, given the temperature it has, that is going to involve a complex story of these parts of some kind that are in the diamond, but is a property of the diamond as a whole, in some sense. And a similar sort of passive property by which it is able to receive certain kinds of light and not others, and by which it might, in receiving certain kinds of light, pass that light on to something else, perhaps fairly reasonably, perhaps by changing it drastically. So whether it's something like the absorption spectrum, sorts of things we have as light passes through some medium, so that it only is actualized insofar as it is receiving something from without, and yet it is actualized in a way that is proper to diamond and different from water or graphite or something else. And I think there's a similar story to say about both the transparency and opacity here. And again, depending on the wavelength, everything is going to be a little bit of all of that. And so there's this particular organization of the energy bands of electrons in the structure of the diamond, which is a kind of proper accident in some particular sense, flowing about what it is to be a diamond and flowing from the diamond having a particular substantial form. But a lot of that story of how it's going to act is also going to depend on what it's acting on further. So insofar as it receives light from something, the actual slowing down or the actual bending of the light depends upon what it's touching. What's the index of the fraction of the thing it's trying to act on? So that's a lot and probably too much, but it's in a certain sense trying to kind of present what a detailed, concrete picture of what a Thomistic notion of what a substance in a chemical substance, the contemporary context would look like, and how we might talk about what light is doing when it is in that thing, and how it is activating that, and how it is, conversation about how it's moving through it, different things like that. But I'm going to stop there because I'm sure I've confused everyone enough, and just leave with this slide of, I've been talking about light, and in some senses sort of intentionally went to a big picture, because to the particle physicist, the visible light isn't that interesting, but to the chemist, it's actually kind of important. And it is a kind of like odd fact about the world that visible light is non-destructive of the vast majority of chemical things that are useful to us, and yet active enough to make them do certain things under certain conditions. And that's exactly the kind of light that we do get from the sun, and the stuff that tends to break down all the chemicals and be really, really bad for us somehow gets absorbed by the atmosphere. So while in the particle physicist vision of light, there's nothing particularly interesting about the visible light, as you get up not just to the question of color, but even to the question of organization of complex biological chemical structures, like organic structures, there's something very interesting about visible light as such. Okay, thank you very much.
Thanks for listening to this lecture on the Thomistic Institute podcast. The generosity of people like you makes this podcast possible. If you enjoy these talks, please consider showing your support at www.thomisticinstitute.org/donate. Your donation of even $1 helps us reach more college students and many others with the powerful truths of the faith, and it ensures that we can keep publishing top-notch lectures on this podcast. Thanks a lot.